Howdy. Okay, homework is due now. So if you have your homework, you can give it to Eduardo. Is here. Anybody? Okay. Thank you. Are there any questions before we get moving? Okay. Today we're going to finish up on causal loop modeling. And you had one problem on the homework to give you some practice. And I would like to spend the next 10, 15 minutes going through an example of a causal loop model. But you're going to do that example for me. And so just a quick recap. The causal loop modeling point of view comes close to the real world because in causal loop modeling we account for cause and effect. Okay, and this cause and effect sometimes can provide feedback through other systems to interact with the cause. So we talked about a causal loop being either negative or positive in the sense that feedback either counters or reinforces the initiating cause. And we looked at a couple examples. One was population dynamics. The other one was dynamics of resistance to innovation. I also mentioned that every time you do causal loop models, you have to define your notation. So make sure you define what the digraphs mean. If you do not define your notation, then it's going to be hard to make sense of your causal loop model. Okay? And there are these other couple examples I asked you to look at. And so what I want to do now is I want you to break up in teams of 3 or 4. Okay? So make sure you're 3 or 4 in a team. And what I want you to do is I want you to make a list of good and bad factors about your hotel stay experiences. Everybody should have stayed in a hotel at one point in time. And we're going to make a list of good and bad things about staying at a hotel that you experienced. I want the youngest person in the team to do the writing. And I'm going to provide you with handouts on which you're going to write. And after you finish, I'm going to collect these. And we're going to have about 10 minutes to do this exercise. And let me pass these out, and then I'll give you more instructions. You have to be 3 or 4 in a team. Okay? 3 or 4 students in a team. 3 or 4. So make sure you find somebody. So we can have 3 or 4 students in a team. So that's 4. You want to join these guys here? Okay, so you got 1 there. Okay. So we have 4 here. Do you have 1?
We have 1, I'm sorry.
Okay. So there's 1. Okay. 1, 2, 3, 4. Okay. So the youngest person is in trouble today. So okay, so we have 4 here. So I'll give you an extra 1. Just write on 1. This is just an extra copy for you to read. So we have 4 students. This is just an extra copy. Okay. Yeah, just write on 1 copy. Okay. Who needs an extra copy? Maybe over here. Yeah, just write on one. Make sure everybody's names are there. Okay, so write down the student names. The youngest person is going to do that. And this is what I want you to do. So you're going to create a list of good and bad factors about your hotel experience. Okay? So what I want you to do is I want you to use negative inversion to construct your causal loop model, which means you're going to create a list of negative factors. Deliberately, when you write these factors, I want you to use a pejorative adjective and a noun, okay? Such as dirty laundry, badly cooked food, low cost efficiency, sloppy service, okay? And I want you to put the various factors together, and then afterwards we're going to drop these bad terms, okay? So I want you to make a list like this. Then when we go to construct the causal loop model, we're going to drop these pejorative terms, okay? Okay, so we're going to have a list of bad and good factors about hotel stay experience. Yes. So you're gonna have a list of bad and good. Yeah. Yes. Yeah, we're still doing this. We're going to come to that next. Yeah, I just want you to make the list, and then we're going to move on to creating the causal loop model in a minute. Okay. Everybody has their list? Bad and good factors. One more minute. Let's finish up. Okay, so let's start with team number 1. So this is going to be team 1, 2, 3, 4, 5, and 6. So team 1, how many bad factors do you have? Just a number, if you can count them for me. 6, and how many good? 8. Team number 2. 5 bad and 5 good. Okay, team number 3. 4 bad and 7 good. And then team number 4.
We have 6 bad and 5 good.
5 good. And then team number 5. 7, 8, and
we have
7 and 6. Okay. Anybody can make any comment based on good and bad factors? Seems we have more good factors, or almost the same. Okay. So next, I want you to use the information that you have created about the bad factors, okay, to construct an ideal causal loop model for the hotel. So this is just going to be ideal, okay? You're going to see why this is going to be ideal. And what I want you to do is I want you to connect the factors in your causal loop model as indicated by the dotted lines on the next page. So you're going to construct your causal loop model using this page, okay? And you're going to choose 3 factors. So you had a list of bad factors, okay? So everybody has at least 3 bad factors. You're going to choose 3 bad factors. You're going to put 1 here, 1 here, and 1 here. Just drop the pejorative term. And what I want you to do is I want you to create a digraph where I have put these dotted lines. So wherever there's a dotted line, you have to put a digraph or an arrow. Make sure you define your notation, okay? So that's what I want you to do now. So we're going to construct a causal loop model about the hotel. It's going to look at the equipment, the staff, the costs, cost efficiency, business revenue, customer satisfaction, and service quality. And the person who's going to be writing now is going to be the person in the team from the nearest city to College Station. Okay? Okay, let's go ahead and do the causal loop model. For the distance learning students, you have to do it yourself. You have to do the writing yourself. Okay? So I have provided both pages, this page and this page, I want you to write on this page. Okay? But make sure you have your diagrams where I have indicated.
Is this where we drop our pejorative chart?
Yeah, you drop them and just put the main factor here. For example, we had dirty laundry. Over here, I just put laundry. Okay, we may be bad food at the hotel, so the issue is going to be food on the causal loop model. Okay? So in essence, we're trying to study how we can improve efficiency for this particular hotel. It's an ideal hotel. Yeah, make sure you define your notation first. Yeah. Start with the notation for your digraphs.
Are we supposed to be doing this one here proportions or negative?
The person.
No.
Mm-hmm.
I thought we were supposed to draw these lines on this one.
Yes, that's correct.
But they're already drawn.
Yeah, so you're going to draw on this one. Wherever there's a dotted line, you need to put a digraph here. So first define your digraph notation.
But couldn't I just define it here, draw a little?
Now I want you to draw on this one. Make sure you have your notation on the same page where you have your causal loop model. Yes.
We're not going, are we going in both directions?
No, causal loop models, you go one direction.
But for example,
Mm-hmm.
you can argue that cost efficiency
Mm-hmm.
can reinforce business revenue.
Yeah, yeah.
But you can also argue that business revenue.
Yes, then you put a diagram for each direction.
So you can have,
Yes, you can have, but it has to be one direction for each
For each
diagram.
arrow.
Yes.
But right here you only have one.
Yes, I just want you to use one.
So can we use either one?
Yeah, you choose which direction you want.
It doesn't matter.
It does.
It does.
Yes.
And so how can we decide which?
You decide. You have a team there.
Yeah, but I'm saying, is there a property or like
No.
a way to pick up?
No.
So let's just go.
Okay, let's wrap up. We have a minute to finish up. Make sure I don't put more than one digraph. Okay, I just want one digraph for the indicated dotted lines. And you're going to choose which direction and whether it's reinforcement or it's going to be opposing. Okay, I'm going to collect the handouts now. The question I want you to be able to answer is this question right here. So take a look at your causal loop model. And what does your causal loop model suggest about improving service quality? Okay, so this is the service quality for the hotel. What should the hotel do in order to improve quality of service? You complained about these things, laundry, food, and 3 other things that you chose. So based on the causal loop model, what suggestions can you provide for improving service quality? Okay, you don't have to answer the question on that piece of paper. I just want the paper now. I'm going to grade the causal loop model, but I just want you to think about the answer to that question. Okay? Thank you. Make sure everybody's name is there. Okay. You have your names already?
No.
Yeah, make sure you have your names there. Everybody's names.
Oh, we were doing it on the wrong one.
Yeah, make sure you write your name. Otherwise, you won't get no credit.
I thought you picked up the one that had her name. You said right on the other.
Like to mess with you guys.
Thank you. Thank you. Thank you.
Do we have to?
No, you don't have to write the answer to the question.
스텝에서 포스트라는 거. 포스트에서 스텝을 포스트에서 스텝을 갔다고?
Thank you. Okay, so I got everybody's solutions. I'll take a look at these this afternoon. Okay, so what's the answer to this question? Diego, team number 1. What does the causal loop model suggest about improving the quality of service for the hotel?
It's just that you have better equipment and better staff.
Better equipment, better staff.
You can improve the service quality.
You can improve service quality. Team number 4. 1, 2, 3, 4. What's your suggestion? Same thing. Anything different from improving staff, equipment?
Improve the customer satisfaction and the revenue.
Okay, how do you improve customer satisfaction?
If the service is better, then the customer's happy.
Okay, so it comes back to this. Okay, so let me make a few comments about causal loop modeling. Okay, so this one is an ideal causal loop model because we don't have much context about this particular hotel. But it seems to suggest that improving service quality is going to increase customer satisfaction. And here is an example of a causal loop model. Okay. This one, you can see that everything is reinforcement. Remember, I defined this as reinforcement. And the solid digraph is going to be opposing effect.
We ran into a question.
Question.
Doing this.
Mhm.
Take away the adjective,
Mm-hmm.
how the staff affects the food. If it's good chefs, it affects the food positively.
Yes.
Bad chefs, it affects the food negatively.
Yes.
When we're drawing our diagram, how do I know if I'm supposed to be doing the reinforcing arrow or the opposing arrow?
Good question. So, for example, you choose food. We're looking at the quality of service, and then we have staff. How is food related to quality of service?
Better the food, the higher the cost.
Yes. So better food. You can assume better service quality. Okay.
Right, but going from staff to food.
Yeah. So staff could be the cooks. It could be the waiters, right? So there should be something about staff that can affect the food.
Or it can affect it both ways, is what you think. It can affect it both good and bad.
Yes, yes. Yeah, I'm coming to that. So it can affect in both ways, right? But if we're going to improve quality of service, then what do we want? We want to affect it in a positive way, right? That's what basically the causal loop model is saying. So to improve service quality, we want to affect food in a positive way, not in a negative way. So that's kind of an inherent assumption there. Okay? So if we improve service quality, then this, according to this causal loop model, it says that it can reinforce business and more profit. Okay, according to this causal loop model. And I should make a disclaimer that the causal loop model is not necessarily perfect. Okay, so this is not the only causal loop model that you can come up with. So the causal loop model is going to depend on the team. Okay, so I forced everybody to be in teams, and that's the essence of causal loop modeling. We want to have a discussion, and based on the team's effort, again we're looking at systems thinking here. You're going to come up with something like this, and then you can now describe what the causal loop model suggests. In this case, you can assume that once you get the revenue, then some of that revenue or profit is basically pumped back into the equipment, the staff. Maybe they are paid more money. Maybe they are given some bonuses or incentives so they can do well. Okay, that's what this is basically suggesting, since we have reinforcement going on here. Okay, so if more profit is put back into the business, then that can lead to improved service quality. But we should also make observations that we can go in the opposite directions, just as was mentioned a minute ago, right? If I look in the opposite direction, the causal loop model can actually spin down, okay, as easily as it spins up. For example, in this case, all the arrows indicate reinforcement, but they can also work in a negative sense as well. If you go backward, right? If there is no, if the staff are not doing well, what's going to happen? There's not going to be reinforcement going on, right? What happens if you reduce service quality? The opposite is going to happen. Cause and effect. So there can be feedback going on. So when we look at this causal loop model, we should realize that this is ideal because there is no external reference to feedback control or cybernetic model. This is just ideal. The only way to guarantee success is basically to maintain this spiral or upward spiral of continual improvement. That's what this is suggesting. This has to go on like this. But this is ideal. Remember when we talk about open systems? This one looks like it's a closed system, right? Nothing is coming from outside. But in reality, we deal with open systems. So this cannot go on like this. Something can happen externally. So we have to think about cybernetic or feedback control as well. It is also important for all the contributing factors to be in place, okay, such as laundry, good laundry, maintenance, food. For example, having good food and maintenance but poor laundry would not result in customer satisfaction, right? Any one bad thing is going to affect service quality. It can spin downward. Okay, everybody following? So, so what's the big deal about causal loop models? The first one is when we create causal loop models in systems thinking projects, we express openly and very clearly the thoughts and ideas that we have. Okay? So that's why I had everybody do this exercise. And the other thing why we do causal loop modeling in systems engineering or systems design is to enable dialogue. Okay, so after everybody started working on the problem, everybody started talking. Right? So if you are working for a large company, you have an issue going on, one way to get everybody providing ideas is to do this, causal loop modeling. So it enables dialogue, and then causal loop models allow for correction and further development. So what you have done, I can give you back, and then you can improve on it, or you can get more information. So it's not just a one-time exercise. When we do causal loop models, it takes time. It's a process. Another point about causal loop models, they are useful for representing the behavior of non-linear dynamical systems, because you can actually see the dynamics when you look at the causal loop model. I can take a causal loop model and I can create a simulation of that causal loop model in order to realize the dynamics of what's going on. Okay? So causal loop models are very important in systems thinking because of these reasons. And also, causal loop models promote and ensures completeness. If I leave out something, somebody's going to say, well, what if this happens? Right? So we need to go back and make sure we account for whatever is necessary. So that's one tool that we use in systems thinking. And you're going to use causal loop modeling when you start looking at your design for the semester project. You're going to think about a societal need, and you're going to design a system for such a need. So in the initial phases, you're going to spend some time doing some causal loop modeling to establish the issues related to the particular needs that you need to meet. Another tool that we use is what we call an n-squared chart or n-squared matrix. Okay, so I'm transitioning now from causal loop models. And by the way, there's going to be a causal loop modeling problem on the exam. I usually put one there, so make sure you practice. And n-squared chart, which is what we're going to do next. N-squared charts are very popular. So if you go and work for any systems engineering company, you're probably going to be using some kind of matrix, such as an n-squared matrix, to do some initial analysis. It is nothing but a table with n rows and n columns, and hence it's called n by n, or n squared. So it's going to have n squared cells. In an n squared chart, which is basically a matrix, we are going to record entities, okay, entities of interest. And then we are also going to record the relationships between these entities, or the interchanges. So the way we do this is we enter the entities in the leading diagonal. So the diagonal is going to have all the entities of interest, and then the relationships or interchanges are going to appear in the other cells. And here is an example of an n-squared chart. So let's, I'm going to have you help me do this one. So I'm interested in studying the relationships between professor, teaching assistant, student, and assignment. Okay. In general, we're going to have entities that are going to represent parts of a system, or subsystems of a system, or components of a system. Okay. So in this case, I'm just looking at this. You can think of it as a people system or organizational system. So in the leading diagonal, I have my entities, okay? And I need to enter the interchanges or relationships in the other cells. So for the cells in this direction, I'm going to enter the outflows. So the outflows represent what's coming out of these entities. So whatever comes out of this entity is going to go in these 3 cells. So there's professor. What goes out of the professor to TA, it's going to come here. To the student, it's going to come here. To assignment, it's going to come here. Okay? And then for the inflows are going to appear on these cells. Okay? This is what comes back. So let's start with the professor, and let's look at professor and assignment. So I need to look at this. What does the professor do that's related to assignment? The professor can prepare the assignment. Okay, they can write the assignment. Okay, so assignment is something such as homework. Okay, and what's the feedback from the assignment to the professor? There may be some interchange between the assignment and the professor, or there may not be. Okay. Okay, so I'll leave this one blank for now. So now I want to look at the student and the assignment. Okay. What does the student do to the assignment? It's going to come here. The student is expected to do the assignment or complete the assignment. So student has to complete the assignment. And what does the assignment provide to the student? The inflow. What does the student get out of the assignment? They can get knowledge. Very good. Maybe that's what provides learning for them. Sometimes assignments can be frustrating. So maybe it can provide frustration, but we hope it doesn't in this course. So anything that the assignment would provide to the student, you would put it here. Okay. So how about let me go to the TA and student. What does the TA provide to the student? The TA can provide graded assignments, or I would just say graded homework. Okay, the TA can provide answers to student questions. And then as far as the student and the TA going backward, the student can ask questions. Okay, so the student can ask the TA questions. Okay. What else can the student exchange with the TA? Maybe the student can provide feedback. To the TA. Okay. We're almost done. How about student and professor? Professor, student. The professor can give instruction to the student. Or you can say provide teaching. or they can provide knowledge. And what does the student give back to the professor? The student can ask questions. The students can provide feedback on how the professor is doing. The students can also give the professor some attention. Right? How about the TA and the professor? The professor can provide assignments to the TA, for example, grading assignments. And then the TA provides the professor with graded assignments or homework. Okay. Anything else? If the TA prepares assignments, then we can enter something in here. Between TA and assignment, it goes there. If the TA doesn't prepare any assignments, we can leave this blank. Okay, again, then we have assignment and TA. If the TA doesn't do anything with the assignment, then we can leave this blank as well. So when you prepare an n-squared chart, you don't necessarily have to fill in all the cells. Okay? You only fill in the cells where there is some interchange, okay? Where there is some interaction. That's where you're going to put information. Okay? It's pretty straightforward. Any questions on n-squared charts? Okay. So you're going to, in the homework, there's an n-squared assignment. And I'll give another assignment in class later. And it's going to be on the exam. You're going to be doing these n-squared charts. Okay. So I want to explain a little bit more about these n-squared charts and why we use them. N-squared charts are very compact, and they enable us to see an overview of complex systems. We can have a complex system, but we can represent it easily using n-squared charts. Okay. Here is an example where we have I have three systems. Okay. So I have system 1, system 2, and system 3. And you can see there is some interaction. So these particular cells, there is interaction going on. And you can see that as long as we have some kind of interaction, then we need to have an interface. An interface is going to be a connection. Okay? So in this particular case, we have interfaces. Interfaces tend to occur in pairs in many systems. Okay? Meaning that you can have one part of the system feeding to another. So you're going to have a pair. Okay? And these interfaces in systems potentially form causal loops. Okay? In this example, you can see system 1 gives something to system 2. System 2 gives something back to system 1. System 2 gives something to system 3. System 3 gives back something to system 2. But also, you can actually see that system 3 is also feeding something to system 1. This is happening via system 2. There is no direct interface between system 1 and system 3. Okay, so whatever system 3 is doing is fed to system 1 via system 2. Okay. Again, this is just by looking at this simple n-squared chart, I can see that. However, in general, when we look at n-squared charts, we're going to have a lot of cells. Okay, they easily get big. So you're going to see this when you start doing your project and some of the exercises. Like causal loop models, it is possible to actually simulate the dynamic behavior of an n-squared chart. Okay, so an n-squared chart is more like a snapshot. Okay, but if we understand the dynamics, for example, what kind of information is being passed and how often, we can actually simulate this. We can build a computer simulation to do that. So interacting systems can easily be represented in an n-squared chart. In this figure, we have 6 interface cells. So we have 1, 2, 2 and 3. They're interfacing, and then 1 and 3. 1 and 3 is not direct interface. So we can represent this as using these causal loops. Okay, there's something going on here. And again, this is basically saying there's feedback going on, okay, or nonlinear behavior. Where the n-squared chart represents a system's internal subsystems, it is important to remember that the whole system is going to exist in an environment. Okay. Again, the concept of open systems says that the system is going to be able to receive inputs and produce outputs, and these outputs are going to be produced as a result of the dynamics of the entities within that system. Okay, so when we draw n-squared charts, sometimes it's necessary to actually show the environment. Okay, so in order to do that, we basically create another layer surrounding the n-squared chart. In this case, for example, I'm interested in this particular system comprising A, B, and C. Okay, so I'm trying to look at this particular system. But this particular system lives in this particular environment. So I'm trying to include this. But I put it in dotted lines because right now that's not my interest. But I'm trying to show the context. Okay, so you can see that my system is now in context in its environment. So we have these shadowy systems, X and Y. Okay, but I'm not focusing on these. I'm just focusing on A, B, and C. For example, this particular system ABC could represent a car. Okay, ABC could be a system representing a car. A could represent the chassis. B could represent the transmission. C could represent the suspension. Okay. Then these other systems such as X and Y could be, for example, X could be the driver, Y could be the vehicle test system, or it could be the road. Okay. So when I want to show the environment or the context for the system, I need to use these dotted lines in my n-squared chart. Okay. Another important thing about n-squared charts is that they actually reveal patterns. So when you create an n-squared chart, you can actually see a pattern going on. Okay. Or you can see maybe configuration. Maybe you can see there's some kind of architecture going on. Remember, all these are system constructs. So when you look at this figure, what do you see? I see that there is system A and B. Okay, wherever there is a circle, it means there is an interchange. Okay, there is some interface. So you can actually see that system A and system B, they are connected. I'm just looking at the n-squared charts, and I'm just making these statements. And I also see that there's a pattern which shows that system D, E, F, and G are actually also connected together as shown. And then in between there is system C. System C is connected to system A, B, and it's also connected to this system D, E, F, G. Okay, so now what we can see are these blocks. Okay, in real systems, usually these blocks are what we call functional blocks, meaning that system A, for example, and system B, they are connected to perform a particular function. Okay, and so we can actually see this pattern from the n-squared chart. Another observation is that with system C, we see that there is more like a waterfall type connection from B to C, from C to D, right? If this were a real system and I need to have interaction between AB and D, E, F, and G, what would happen if system C fails? If I knock out system C, what's going to happen? Then this entire system may not be able to function as required because system C just is the only link between this block and this block. So that may be a bad thing. We may need to add some redundancy in the system. But I'm just looking at the n-squared chart and I can make those statements. Okay? So the n-squared chart can be a very valuable tool for amassing information about a complex system or project. Another thing that you can do with n-squared charts is you can interchange these entities. Remember the entities on the leading diagonal? I can interchange these and I will come up with a different pattern. Okay? And this particular arrangement, A, B, C, D, E, F, G, actually represents or reveals these patterns that I just described. Okay? If I change A, B, C, D order, it's going to change the pattern, the entire pattern. So when you create an n-squared chart, you should keep in mind that you can change the order of your entities in the leading diagonal. And that's going to affect the outcome of the patterns or the interfaces that you're going to have in your n-squared chart. I want to introduce another concept in systems thinking, which is known as encapsulation and elaboration. Okay? Encapsulation, as the word implies, it means you are encasing something. Okay? Elaboration means you are basically expanding. So this is a very important concept in systems engineering because it allows us to think about these blocks as one entity. Even though it may have several subsystems within the block, we can look at it as one entity through this idea of encapsulation. So the functionally bound block, for example, systems D, E, F, and G, which is this one, you can think of this as one system. We can call this particular system Q. Okay? Through the concept of encapsulation, I can assume that Q is just one system, okay, when I'm looking at it. So I can actually draw another n squared chart with this system D, A, E, F, and G encapsulated. So I can do it this way. So I have my original system A, B, and I have C. And now, instead of representing the entire block, D, E, F, and G, I'm just going to represent it as Q. Okay, why can I do that? Because of this idea of encapsulation. So when we do encapsulation, we basically hide. We hide the contents of a system. We hide them from the outside. Okay? We hide the contents of the system from outside because when I'm drawing this n squared chart, maybe I'm not interested in looking deeply in this particular system Q. If I'm interested in actually seeing what's inside Q, then I can do an elaboration, which is the opposite of encapsulation. So if we do elaboration, then it means that we go back and review the contents of a system. The reason why we do encapsulation for n squared charts is because of simplicity and clarity. Encapsulation reduces the perceived complexity. Okay? If you are drawing n squared charts, you don't have space. You can actually draw an n squared chart on several pages. You can start with this one, and then you go to the next page. You may just focus on Q, okay? Or you may focus on this whole system. Okay? Again, the concept of encapsulation and elaboration is very important in systems modeling. So when we start doing systems modeling, I'm going to talk about, I may talk about encapsulation again. Okay? Any questions on encapsulation? Okay, that's good. Another comment to make here is that when we do elaboration and encapsulation, keep in mind that we have to maintain the environment, we have to maintain the interfaces and the interflows between the entities. I'm not changing that. Everything is maintained. Okay? So in other words, this representation of system D, E, F, and G by Q implies that Q is going to just behave as this entire system. Nothing is going to change. Okay, here is an example of a bit more complex n squared chart. This is an n squared chart for air traffic management system. This is for an air traffic management system. So let me just quickly highlight a few things about this n squared chart. The entities in the leading diagonal are as follows. The first one is aircraft general flying. So this is a system that's going to do that. Then there is an aircraft approaching airfield. There is landing and taking off. Then there is controlling airspace and controlling approach, takeoff. Okay. Then there is controlling ground movements. And then there is another entity, aircraft taxiing. And then the last one is ground marshalling. So when we look at an air traffic management system, it comprises these entities. Okay? So, for example, when an aircraft is flying, in general, there's going to be this system which is going to monitor that aircraft. Okay? So this particular system sends information to, again, I'm just reading the n-squared chart. So it sends information to controlling airspace. Okay? So this is the outflow. It goes to controlling airspace. And the aircraft provides the status. It provides its position and its vector, because it's moving, it's flying. And the controlling airspace system provides information, the data, back to the aircraft. And it provides warnings and maybe rules about this aircraft. Okay? So when the aircraft is approaching an airfield, we have this other entity or system that takes over. So for this particular aircraft approaching airfield, the aircraft is going to send its status, vector speed, its height or altitude, and this is going to go to controlling approach or takeoff. Okay? And the controlling approach or takeoff is going to provide feedback to the approaching aircraft. In this case, it's going to provide corrective actions. Right? It's going to also provide the airfield data back to this aircraft. So you can see what's going on here. Okay. The next one, landing and taking off. Again, you can see that landing and taking off, you're going to have to use this controlling approach. The aircraft is going to provide the status and the other aircraft data. And the controlling approach takeoff entity is going to provide the airfield data. You can see that the controlling airspace hands over to this approach. So there's a handover. And this controlling approach takeoff gives feedback back to the controlling airspace, saying that it's going to take over from ASM. ASM is the airspace management system. Okay? And so on and so forth. So the aircraft finally gets onto the ground. Controlling ground movement of the aircraft is another system. And when the aircraft is taxiing, there's another system that controls that. Finally, when the aircraft lands and gets to the gate, there is another system, which is the ground marshalling, which directs the aircraft as to which gate it should go and where it should park. The aircraft taxiing provides cooperation. So to the ground marshalling gives instructions to the aircraft where to go and what to do. Okay? So besides being holistic and synthetic, meaning we can actually build these things, these n-squared charts, one thing you can actually see here is this dynamic nature. Okay? There is some dynamism involved in this n-squared chart. And like I mentioned earlier, I can take this n-squared chart and given more information about these entities and the dynamics, I can create a simulation of this system if I'm going to study this particular system. So one other tool that we use a lot in systems is simulation. Okay? Simulation is a big part of systems engineering. Even though in this particular course, simulation is not required because we mainly focus on the theoretical aspects. But the next step up is to take whatever we design and simulate it. So we're going to do some modeling, which allows us to build simulations or system simulations. Okay? So let me make a few comments. I'm running out of time. Creating n-squared charts actually can be automated. So you can use software to do this. We don't usually do that. Those of you who've taken facilities planning 416, if you remember, You used layout procedure designs, some computerized software, where you were trying to decide on the layout, right? So you look at the adjacency of the different entities within your layout, and you try to find the best layout, right? So the same idea can be used for creating n-squared charts. Here's an example of an n-squared chart, okay, which is given right here. You can use software to give this a score of the adjacency. How cluttered is this? You can give it a score versus another one. See here I have E, I, C, G, A, H, D, B, and F in the leading diagonal. Over here, you just rearrange these in this particular order, and you come up with this particular pattern, and you can actually see it here, right? So this particular pattern tells me a lot, because I know that system A, B, and C create one functional block. Similarly, we have D, E, and F, including C and G, and then we have G, H, and I. System C provides a link. Same system G, they provide a link. Okay? So when we are designing for C and G, we have to keep in mind that these provide these important links within this particular system. Again, we can say this just by looking at the n-squared chart. I'm not going to spend time on looking at systems thinking case studies. So what I have done is provide you with just an assignment so you can get a feel. There is more to systems thinking, but I tend to stop right here on systems thinking. There are other methods. One of the methods is known as the rigorous soft method. Another one is called the generic reference model. And in homework 4, you will find a write-up, a description on what this system is, what this method is rather than this one, the generic reference model. I just want you to get an idea that there's these other methods in systems thinking, and you can read on your own. And the homework is meant to have you actually practice writing n-squared charts as well as causal loop models. And they are in the context of a system thinking case study. Okay? So that's what we're going to be doing this week. And then Thursday, we're going to start modeling. So I said you should make sure you review your set theory. So we're going to start doing some math starting next week. This week, rather, Thursday. Okay? Okay, thank you. Yeah, sure.